Good morning and welcome back to the International Test Conference 2021. I'm Yervant Zorian and I'd like to start this plenary session 3 together by few announcements and also introducing the first keynoter of this session. I'm very pleased that you had a successful 2 days of ITC already and looking forward to this third final day of the conference. But also in the evening, we are starting 2 workshops in parallel. The arts workshop, automatic reliability, test, and safety, as well as the new workshop on SLM, silicon lifecycle management. I know many of you are registered. Just in case you haven't done yet, you still have the opportunity to do so during the day and be ready to participate in the workshop today starting at 3:30 p.m. and tomorrow all day long. Now, I mentioned at the opening session that we do have this the highest level doctoral thesis of the year award, which is named after Professor McCluskey. And we do a selection over 2 steps at 3 conferences during the year. And then the finals happen here at ITC, which took place yesterday. We already have the winner of that. So what we did is we used 2 sets of judges, academic and industrial, and we looked at the global coordination and the local coordination in these 3 conferences, happened to be VTS, ATS, and ETS. And the winner is Lizu Wu. Lizu, congratulations. We're very pleased that you happen to be the winner this year. You have the best doctoral thesis of the year. Lizu comes from Delft University of Technology, and her work in MRAMs was the winner. This work has been presented first in the competition at ETS as semifinals and won the award here at ITC. Now we can move to the second award that I wanted to bring up today, which is the Best Paper Award of JETA. So JETA and TTC collaborate together, as you know, and we select 1 paper every year from JETA of that previous year, basically, of 2020. And this year, I'm pleased to announce the winner to be Ankush Shrivastava and Prakash Ghosh, both of them from IIT Bombay. And their work is a novel approach of data content zeroization under memory attacks. Okay, it's a security paper. It's a very strong paper. Congratulations, Ankush and Prakash. Now I have the pleasure to introduce our keynote speaker. We have a very distinguished speaker today with us who will be addressing a very timely topic, addressing design challenges in the era of SysMoore from architecture to silicon lifecycle management again. So Shankar is the general manager, as you see, of the digital design group at Synopsys. He's a member of the corporate staff. His responsibilities in this group encompass place and route, test automation, formal verification, and so on. Previously, he was the senior VP of Digital Implementation Group, and he oversaw the development of game-changer innovations. Fusion compiler, RTL architect, TestMax solutions, 3D IC compiler. With his 25 years of experience, Shankar has seen a number of things in the past. Before 2017, he was part of Mentor as a general manager of IC Design Solutions division. He went to Mentor with an acquisition of his company, the one he founded, Sierra Design Automation. And then prior to that, he was with Synopsys starting 1992. Shankar has a master's degree from UT Austin and also has a bachelor degree also from IIT Bombay. Shankar, the floor is yours. Thank you.
Thank you, Yervant. And let me start by extending a heartfelt thank you to ITC for inviting us to present this keynote today. The title of my talk is Design Challenges in the Era of SysMoore, and I'm sure you all are wondering, what is SysMoore? So let's go into some details to understand what exactly is happening in the environment around us in semiconductors. We are in an exciting age for semiconductors across many market verticals: networking, data center, mobile, automotive, and new emerging ones like AR, VR, and Industry 4.0, digitization is here to stay. We are almost seeing a decade's worth of progress that has been made just within a few years as AI and ML and big data pretty much permeate all these verticals with respect to driving innovation, improved workflows, and improving the overall performance and productivity of many, many applications. Now, obviously, all this is translating into a large number of design starts in the semiconductor industry, and you can see the robust structural demand in semiconductors that is going to last for the next several years. This translates into some key trends that we must be cognizant of as we are trying to support the semiconductor industry with innovations. The first one, of course, is very well understood. It's PPA, which is performance, power, and area. But also let me add two more letters to it, C and T. C is the cost, and then T is the total time it takes for execution. So PPA CT is important across all market verticals, and the push for that is relentless. The second is the advent of custom silicon. I mean, this is truly the golden age of computer architecture. There are many, many new domain-specific architectures getting created for different types of workflows and problem statements. And so a lot of exploration and a lot of architecture work going on. Third is the vertical integration, right? Looking at the entire stack from software to silicon or even down to atoms to figure out how to improve performance of systems is also a big area of focus across many different companies. And then let's add on another layer, which is vertical specific needs and challenges. For example, in the data center space, secure silicon is becoming very, very important as multiple companies are providing confidential compute type of architectures. In the mobile space, die area per watt. In the automotive space, safety, resilience. And so each of these verticals brings their own set of specific challenges that we need to overcome. And all this while the total number of VLSI design talent is not growing at the same pace. So we also have a significant productivity challenge where that structural demand is not being met by all the VLSI talent. So we also need innovations on the productivity front. Let's now look at the technology trends to support this structural demand. So for almost 3 decades now, we have benefited from this amazing exponent of Moore's law, and that has created hundreds of billions of dollars of market capitalization in semiconductor companies. But looking ahead, we definitely see some interesting trends. As we go to the advanced nodes, we see that density scaling is alive and well, but performance and power scaling is starting to peter off at the 15 to 30% range. While all these applications are still craving for more performance and more per watt. So how do we apply a booster pack to this classic Moore's law in order to solve this gap? And this booster pack is what we at Synopsys are calling SysMoore. And it really comes from the addition of 3 specific concepts to the traditional Moore's law execution. The first one is, of course, domain-specific architectures. We're seeing it all around us. And by just fundamentally going back to architecture to come up with custom architectures to solve specific problems, there are big gains to be made. The second one is, of course, 3D IC, or the whole evolution of multi-die systems. And by enabling that, we are able to really elevate system-level performance significantly. And then last but not least, I mean, AI is sweeping many, many industries. Why not ours? And so application of AI to EDA and to the whole design flow and methodologies also offers many, many opportunities to help us bend that curve back and give us the kind of gains we are looking for. And then overlay on this the engineering cost, which is skyrocketing up as you go from node to node and do more and more complex designs. So we really have to solve these twin challenges of performance power as well as productivity in a different way as we look ahead in the SysMoore era. So at Synopsys, we have established a very ambitious roadmap in order to solve these problems. And the reason you see that X in the middle is that the roadmap has 6 vectors, and we believe the multiplicative effect of these 6 vectors is going to make a dent towards meeting these challenges. So first and foremost, how do we support the industry's transition to domain-specific architectures with rapid exploration tools to help designers rapidly look at the PPA implications of their decisions, both at the architecture level as well as at the RTL level. Second is, of course, enabling the energy efficient design methodology. Really, at this point, per watt is one of the overriding metrics that every design team is looking at. And so how do we optimize power and energy from a software to silicon perspective with an end-to-end approach versus just doing a little bit in some parts of the flow? Third, our foundry partners are continuing to innovate and driving that scaling as we're going from node to node. So how do we support them with respect to all the node evolutions? And there are several new exciting concepts coming up there, like the new types of transistors, buried power rails, mixed row, and so on. Then, as the industry evolves to multi-die systems and stacked die architectures, there is a lot of work to be done in terms of creating a whole ecosystem of designs, methodology, tooling to support those types of designs with a high level of efficiency. Another key metric or vector to look at is really the silicon lifecycle. Increasingly, the ability to monitor in field and to monitor the performance of devices in field and monitor the resilience of devices in field is becoming very, very important for specific verticals like data center, automotive, IoT, and so on. So being able to really track the health of the silicon across the entire life cycle, from design through test, through production ramp, all the way into in-field, is very important to improve the quality of the design as well as the quality of the performance in field. Last but not least, cloud and AI is disrupting many industries, and it offers many opportunities in our own industry with respect to improving workflows and improving results. So this is really the 6 vectors we are innovating on. And let's now take a look at a few of these to understand it in more detail. So let's now start with the design flow. Our design flow for many, many years has been a traditional sequential set of best-in-class point technologies. You synthesize your design, you insert test, you do some incremental synthesis, then you do place and route, and then you do sign-off. Unfortunately, this flow is extremely stressed and it's breaking as we are going from node to node, with more and more effects being essentially coming up from the device layer, from the physics layer, from the process layer. And this is making the flow extremely non-convergent, which is resulting in many, many loops. For example, the introduction of test logic is essentially causing the design flows to be not very convergent because of the significant congestion that we may add to the design or significant timing closure challenges that may be added. So the current design flow is very iterative. It requires pessimistic margins to predict what may happen downstream. And also the overall PPA is significantly below par because of all this iterative and all this heavy margining that's needed. So we need to evolve this to the next level. And really the solution is to move to a hyper-converged architecture. What does hyper-converged mean? Just like in the data center space, right? 3 different disciplines like compute, networking, storage were fused into a single hyper-converged architecture to dramatically improve the total cost of ownership. We can bring the same concept to the EDA world and essentially fuse all these different spaces of synthesis, place and route, sign off, test, all on a single data model, and then enable a much higher quality of results and a much more convergent and predictable flow. This architecture is what we call fusion at Synopsys. And we have been executing on this for the past decade, and we are seeing excellent results at customers as we are fusing all these technologies to create much more convergent flows, remove margins, drive significantly higher PPA, and most importantly, significant improvements in terms of time to results and size of designs. One example of fusion as applied to the DFT area is the traditional DFT flow. You would synthesize, then you would add your test points, or you would add your scan connections. That would cause a whole bunch of congestion issues, and then you would have to react to the congestion issues, which would then impact the predictability of your flow downstream. With the fusion approach, with DFT natively integrated on the same data model, the algorithms tightly aligned between the placement steps and the scan hookup steps and the test point steps, we are now able to produce dramatic improvements with respect to the routability of designs as well as the convergence of the flows as we bring synthesis, test, and place and route all together in a single fused approach. Another area is really test quality. This is again something that has to be looked at end to end, and especially as we are going to the latest nodes with FinFET, the importance of catching defects and having the right fault models is becoming greater than ever. So again, a lot of innovation needed here as we go from node to node. So if you look at cell-based testing, the importance of at speed transition as well as slack-based transition faults is very, very important. When we go to ultra-low DPPM applications like automotive, the importance of cell aware is very important. And then when we look at memory, the importance of really being able to predict the SRAM bit cell failures due to process variation or telegraph faults due to repeated read-write access of memories. All this needs to be added to our fault models as we are going from generation to generation. And this is, again, an area of major focus and investment at Synopsys. Let me now move to 3D IC design. And I'm sure we are seeing it all around us as we go to different applications like networking, HPC, or artificial intelligence chips. 3D IC and multi-die integration is very, very pervasive. Whether it is to optimize latency to IOs, optimize latencies between dies, optimize latency between die and memory, this is becoming the preferred way to improve system-level performance. However, if we look at the workflow to implement these multi-die systems, it's extremely challenging because there are a lot of handoffs between the die-level designer and the system-level designer in terms of getting the pinouts and the bumps and the alignments correct, handoffs between the sign-off team and the power, thermal, noise integrity teams, because there is a dependency between all these different areas, and these are all kind of isolated in silos, and there's a lot of handoffs needed. The complexity in terms of DFT for multi-die skyrockets, and so that needs to be considered in a very special way. So it's a very fragmented approach today and a high level of inefficiency. So if we have to summarize the challenges with doing 3D IC designs with the current generation, it really is fragmented point tools, poor abstractions, the inability to scale to hundreds of thousands or even millions of connections at the multi-die level, and the lack of co-design and convergence as we look at the different levels of hierarchy. So we need something new, we need something different to get ready for this 3D IC era that is rapidly arriving. So our approach is really to take a holistic, unified approach to designing multi-die 3D ICs. Just like SoC level design needed a fully integrated approach, 3D IC design needs a fully integrated approach. And so we essentially built on top of our IC data model the ability to rapidly explore different 3D IC configurations and automatically partition 2D netlist into 3D based on connectivity and other performance factors. The ability to create 3D IC designs in a very intuitive way and do a lot of what-if analysis where a large monolithic SoC may get split up into multiple dies at different nodes, and so there is a lot of what-if analysis needed. The actual task of design construction, where we need automatic routing of all the interposer connections, we need to do bump creation and connecting up the micro bumps to the pinouts, and of course, inserting DFT across the multiple dies. And then, of course, the ability to analyze as we design. So the access to all the system level analysis tools like EM tools, thermal tools, power integrity tools, while you're in the process of implementation is also very, very important. So our approach is really a unified approach, and this is what we call as 3D IC compiler. And we're seeing rapid success with this as the industry moves to this new paradigm of designing multi-die. Specifically around DFT support for multi-die designs, we're really excited about the support for the IEEE 1838 within our TestMax family of products, and the ability to reuse the high-speed I/O interfaces to reduce test time, as well as high-speed die-to-die interconnect test and repair capabilities gives us a lot of opportunity to bring new innovation into the ability to test these 3D ICs. Now, functional safety is a big care about for several applications like automotive, medical, and others. And very similar to what we saw earlier, it has to be the introduction of the functional safety logic has to be done in a very convergent and a very systematic way across the flow. And so we have built an end-to-end FUSA flow that pretty much starts by capturing the functional safety intent, and then using tools which do the SPFM analysis, we are able to automatically detect all the areas where we need to introduce the TMRs. We have automatic insertion of the DCLS capabilities, and then all this logic inserted has to now be convergently implemented across the entire flow through synthesis, PNR, and sign-off. So this, again, has to be done from an end-to-end perspective and not just a point tool type of a perspective. If you look at functional safety now at the subsystem and at the SoC level, we really have to think about functional safety across 4 different phases: manufacturing test, the power on, power off self-test, the periodic checking, and the online monitoring. So the architecture that we have enabled to sort of make this happen, it really starts off at the component level, where you, of course, start off with your memory BIST around the memories, your X-tolerant LBIST, and the path monitoring units for the logic, testing for your DDR5, your PVT controllers. And then we need to have a fabric that basically controls and extracts the data from all these subsystems all the way up to the subsystem layer or the full system layer, and that's the whole SHS connectivity layers and fabric. And then for each type, on each phase, we basically implement the functional safety protocols either through the tap ports or through the sequencers or through the safety managers for the periodic checking, or even through the firmware for the online monitoring. So this type of a full SoC level architectural approach is absolutely essential to implement functional safety in designs. And many of these components are being actively used on SoCs designed with Synopsys today. Let me now move to security. And very similar to the theme of this talk, we have an end-to-end approach that is needed. We were really excited to be picked by DARPA as the prime for the AISS program, and we have a large ecosystem of partners and several universities working with us with respect to delivering this solution across the verification, IP, as well as the digital design spaces. And very similar to what we saw earlier, we need an approach that starts from architecture exploration and goes all the way through placement and routing to insert these structures for secure silicon, and then to basically do a lot of checking and a lot of safeguards to ensure that we're not susceptible to different types of attacks. So it starts with very early analysis at the architectural level to identify vulnerabilities, inserting registers and all the security infrastructure at the RTL level, support for watermarking, obfuscation, logic locking, and so on. These are all structures that are inserted at the RTL level. And then all these structures, their intent has to be preserved through the entire implementation flow. And as you get closer and closer to the end of the flow, there are very specific types of things one has to do to implement secure silicon. So really this end-to-end approach is needed in order to really make this a reality. And as I mentioned earlier, with so many market verticals now very, very keen about implementing these types of secure silicon structures, we have a great opportunity to really build on top of what we have already done with safety to do the same thing for security. Finally, let me just tie this all together with our vision for silicon lifecycle management. It's very clear that for several market verticals, right, automotive, data center, IoT, others, the importance to look at the operational metrics during in-field operation and then learn from those metrics to either adjust the in-field operation or to even go back and improve the next rev of the design is very, very critical. And so we can no longer be blind about what's happening within the chip during the in-field operation. And we need to have deep visibility, and then we need to harvest that data to go back and improve the entire life cycle so that the successive generations of designs are improved. So our vision with respect to the silicon lifecycle really spans all these different areas, right? We basically want to start a design by inserting certain structures into the design. We want to harvest data from these structures and other areas during the whole chip production process with respect to looking at the parametric yield failures and other types of metrics, test coverage, etc. We want to look at the system bring-up phase for rapid debug, as well as we want to optimize in-field performance and extend the mean time to failure with adjustments in field. So this really needs us to stitch together all these phases, which are traditionally very separate and very siloed, with an approach that really harvests data across all these phases and ties them together end to end. And so we have an exciting array of capabilities to enable this to happen. Obviously, we start with inserting the sensors in chip. We have some very strong PVT sensor technology, which is widely used in the industry, and we're working on several other types of sensors and monitors. Then we have our Fusion design platform to basically guide the placement of the sensors in optimal locations, as well as to insert the sensors in a very PPA neutral way, because these sensors and monitors can essentially end up being quite a significant amount of disruptive logic. Then we have our capabilities around the whole volume ramp analysis and rapid diagnosis of parametric and other types of yield failures. Then we have our big data approach to silicon analytics, which allows us to really be able to look at a large amount of data coming from all these phases and rapidly kind of derive insights. And then last but not least, the high-speed access and other test IPs to pull the data off chip quickly so that we improve test times as well as improve in-field performance. So here's an example of how all this comes together. By introducing our process, voltage, temperature, sensors, monitors, many customers essentially do the readouts of all these PVT sensors and essentially implement schemes like dynamic voltage frequency scaling, temperature throttling, and we are now even moving further up the stack to be even able to kind of look at the monitor these chips during the operation, and also influence the software stack above it to essentially update and optimize its performance. So a lot to do here. It's a very, very broad space, multiple domains, but by connecting them together, we believe that we can really deliver significant gains in every one of the individual phases, and most importantly, improve the resilience metrics like the mean time to failure. So finally, let me conclude by just summarizing that we are in this amazing bull run for semiconductors. A multi-year structural demand exists, but we have to solve all these challenges in order to be able to enable that as an industry. The need for PPA CT, safety, security, resilience, all this needs end-to-end solutions. We really cannot do point solutions to solve point problems. We have to take a much more expansive view because everything is getting interconnected. And this, triple play of Fusion from a whole design platform perspective, this SLM approach, which is a multi-dimensional approach to improve operational metrics, and then designing in security and safety very natively are all key to addressing some of these demands. With that, I conclude my presentation and happy to take a few questions. Thank you.
Thanks a lot, Shankar. This was really a very impressive presentation. You covered it end to end. It was very comprehensive, from the design and the complexities of the design, how it should be handled, all the way to the life cycle and the resilience of the chip. It's true. I mean, ITC, after all, cares about the health of the chip, right? We have covered systems also in the past, but mostly semiconductor health at this point. And what you covered is all the aspects of that health: safety, security, tests, quality, and so on. They all complement each other. In the interest of time, we will not take questions. We'll move on to the next speaker. But again, congratulations for this excellent talk. We have it recorded, and if somebody wants to watch it again, or some of us, if we have missed it, we'll be able to see it later on as well. Thanks again, Shankar. We appreciate that.